Start recording. Okay. So good afternoon, everyone. Thanks for joining. Today we'll have Arpita Mitra from ISER Bhopal. She'll going to be talk about soft factors in the presence of small negative cosmological constant. Over to you.
Hi, first let me begin by thanking the string group at IISc for giving me the opportunity of presenting my work. So today I'll present about soft factors in the presence of small negative cosmological constant, and this work is done with Dr. Navamita Banerjee and Karan Fernandez and Arindam Bhattacharjee, who are postdocs at HRI. So my talk will be based on these references. The first work is nearing completion, and the other two works are my recent publications. So first, I will start with a brief motivation and overview that what we are doing. So long time ago in 1960s, we all know that Weinberg proposed the soft theorem, which tells us the factorization of an amplitude. So if we have an amplitude with which involve one or more soft particles, and then we can factorize this amplitude as a soft factor into the amplitude only having the hard particles. So the in right hand side the amplitude Mn has only corresponds only the hard particles, and Pa are the hard momentum, and in the left hand side Q is the soft momentum and epsilon is the polarization. So this expansion is valid only when the photon or graviton energy is small compared to the other finite energy particle momenta Pa. And these soft factors are known to be universal in flat spacetime up to leading order in frequency for photon and subleading order in graviton. They are also invariant under gauge transformations. So soft photon factor is invariant under gauge transformations, and soft graviton factor is invariant under general coordinate transformations or diffeomorphism. So in recent works by Strominger and its collaborators, it has been well established that there is a relation between asymptotic symmetry, soft theorems, and associated memory effects, which is known as the infrared triangle in the literature. And this exists for both the gauge and gravitational theories in asymptotically flat spacetime. But analog of these soft theorems on spacetime with a cosmological constant are not well understood. But we know that in the presence of cosmological constant also the gauge invariance remains intact. So we expect that there should be a version of soft theorems for such spacetimes in a certain limit. And we also know that if we consider asymptotically ideal spacetime, for instance, there exists no asymptotic null boundary and the usual asymmetrics is not well defined. These spacetimes also have a cosmological constant, so there already exists an inherent length scale that prevents us to define a zero frequency limit, because we know that if we consider a scalar field on this background and we will get a quantized discrete spectrum, and the frequency will be proportional to the conformal dimension of the dual operator of the CFT. So we just can't take omega tending to zero limit.
So
So
hold on, one second. So as a gauge invariance remains intact, why is that the reason for this?
because the physical processes are same. So if we are considering a photon scattering in ADS spacetime, it has to be invariant under the gauge transformation of like epsilon goes to epsilon plus k.
No, but I'm saying like if you have like so the statement about soft theorem is a statement about low energies, right?
Yes.
So what I'm trying to understand is why is the gauge invariant? So everything has to be ultimately gauge invariant. That is true, but why gauge invariance is the motivation for arguing that the soft theorem should exist? Because if there is some other scale in the problem, I would probably not expect that soft theorems are there, right? For instance, in the case of ADS.
Yes, so in that way, like, yeah, only just omega tending to zero will not give us the, like, we are not expecting just the flat space-time soft limit, yeah. So as there is a scale, so the soft limit will be something like a double scaling limit, where like omega goes to zero and at the same time L goes to infinity. Yeah, so it is not like the omega goes to zero is the soft limit in the presence of this scale.
Yeah, okay, but I'm just
Yeah.
saying that the question of gauge invariance, I mean, why is that significance is something that I did not quite follow, but maybe I'll ask you again later, so go ahead.
Okay, okay. Yeah, so we just thought that as we are considering some physical processes, and if we get a scattering amplitude, and if we are not taking a vanishing frequency limit also, so if it is an, so in this limit we expect a gauge invariant answer, like whatever double scaling limit we are proposing, or like it is already proposed in we want to get the flat limit of a like in ADS-CFT correspondence, if you
Yeah,
are
no, yeah,
considering a yeah, yeah. So
yeah,
that way,
that's
yeah, yeah. Yeah, sorry. So, yeah. So, keeping this in mind, we have derived the leading 1 by L square perturbative corrections, where this capital L is the ADS radius of the flat space time soft photon factor. So, initially, what we have done, we consider the cosmological constant as a small perturbative parameter. So, whatever results we got, that is like corrections to the flat space time result. And as we, sorry, as there is no Yeah, so as there is no notion of quantum scattering, quantum asymmetrics that way, so we first calculated the soft factor using the classical soft theorem, which was proposed by Sen and Ladha in around 2017 and 18. So we use the classical soft theorem to calculate these cosmological constant corrections to the flat space-time soft factor. So as I've already mentioned, so to finally calculate the soft factor, we will require a double scaling limit. So the double scaling limit means that we will consider a vanishing frequency limit when the ADS radius goes to infinity, keeping the product of them finite and large. And then we do a backtrack. So in general, whatever we are doing, we are trying to infer a quantum soft factor, or like the universal soft quantum properties from this classical result. So we have seen that the 1 by L square corrected soft
So
here.
can you go up a
Sorry,
little
yeah.
bit? I just want to understand. See, I think you should go slightly slowly in the first couple of slides so that
Oh, sorry, sorry,
what
sorry.
is going on. Then after that,
Okay,
you can
okay.
accelerate. It's fine.
Okay,
So
okay.
so we have so the what does it mean to say that? So what do you mean by 1 by L square corrections to flat spacetime? But L is basically changing the structure of the observable, right? So you're instead of having S matrices, now you'll have correlation functions. So I'm a little bit confused
Yes.
about what do you mean by correcting 1 by L square correct. So what are you constructing the 1 by L square corrections around? Is it around the flat space calculation or is it around?
It is around the flat space calculation. So just, I think this figure will be more like it
Okay.
will help us to clear
Okay.
things
Probably.
up.
Yeah. Okay.
Yeah. So should I explain this figure now, or?
Yes, please go ahead. Yeah. I mean, I'm just trying to understand. Maybe as you explain the calculation, maybe it will become clearer. So I'm just trying to understand how can
Okay.
what is the systematic 1 over L calculation you're doing is what I'm trying to understand. Because if in flat space there is S matrix and in ADS there is a correlation function. So how
Yes.
are
So
you
the
construct? Yeah.
Yeah, so there is this asymptotic mapping.
Mm-hmm.
So if we consider the ADS space time, so here in this red fringe, so this is like a global time of this tau equal to around tau equal to pi by 2, and we can parameterize here as tau equal to pi by 2 plus u by L. And this blue fringe is like the tau equal to minus pi by 2 and plus or minus u by L. So when we are taking a L tending to infinity
Can you
limit,
move the thing a little bit down because I cannot see the top part of the slide. Move a little bit, the
sorry,
top part where you have written something, I can't see it. Right.
now,
Yeah, it's better.
okay, yeah. Yeah. So this is like the asymptotic mapping. So I have a ADS space time, and then I am taking a large L limit. So if I am taking a large L limit, we will go to like, we are sort of zooming in to the center of the space time where there is a flat space time patch. And how do we map these things? So the mapping is like the red fringe over the left, in the left figure around tau equal to pi by 2. That will map to the scry plus of the flat patch, which is at the center of the ADS, and this blue region at tau equal to minus pi by 2, that will map to scry minus on the right hand side. So this flat patch is actually at the center of the ADS space time. And these, so if we have a massless particles, so that massless particles will go to this, the outgoing particle will go to this red fringe. And if we have this massive particle, so this massive particle will go to this Euclideanized global time area. So that is like delta m plus. So the massive particle will go there. So is it now understandable? Like so.
So
Yeah.
I'll just ask it this way. So basically, in asymptotically ADS spacetimes, you'll have some set of fall-offs at for your ADS. That's the definition of asymptotically ADS. So I would
Yes.
expect that what you are basically doing is to take some scaling limit which involves L and the radial coordinate in the ADS, in the asymptotically ADS region, in such a way that you end up with asymptotically flat behavior. This is what
Flat behavior around the center of ADS. Yeah. So sorry.
right.
Yeah. So
No,
actually, I have
you can,
explained.
yeah, you can,
I think one
yes.
sec.
No, I think that go at your own pace. I didn't mean to destabilize your talk, but
Yeah. So
I'm
this
just
is
trying to.
the. I think
Yeah.
now it will be clear. Yeah. So if I write this global coordinate, and then if we do a coordinate
I see.
transformation,
Okay. Yeah, that's good.
and then
That's
if
good.
we
Thank you.
take a L tending to infinity limit, we zoom into the center and we
Okay.
get a flat patch.
Okay. Thank you. Yeah, you can go back to the. Sorry to because if I don't understand
So,
what is
yeah.
happening in the beginning, I won't understand anything. That's why I'm asking.
Sorry.
Sorry.
Yeah. Yeah, so then that was our plan. So whatever we have done, so in the first we have calculated a soft factor, like sort of a 1 by L square perturbative correction to the flat space time soft factor using the classical soft theorem. And then from that soft factor, as we know that soft factor is universal in leading order, so we have assumed that that fact is holding for ADS spacetime also. So we tried to write 1 by L square corrections to the flat spacetime large gauge odd identity using this soft factor which we calculated using the classical soft theorem. And at the work which is nearing completion, there we are trying that to get this 1 by L square corrected soft photon odd identity from a CFT odd identity, like the boundary CFT odd identity in the large ADS radius limit. So this work in order L0 order was already done by Hijano and Neuenfeld. So sort of we are following their prescriptions, and we are trying to find that similarly the 1 by L square corrections of the photon factor what we derive can be achieved in the large L limit. So I have already mentioned that these large gauge odd identities on ADS boundary have an identification of the flat space-time patch, which is at the center of the ADS. And this asymptotic mapping is like this red fringe, which we can parameterize as tau equal to pi by 2 plus u by L, where u is the retarded normal, in general the retarded Minkowski time t minus r, and that will be mapped to a null infinity sky plus. And similarly, the blue fringe will be mapped to the sky minus. And these shaded caps, that will be the analytic continuation of a boundary CFT in the imaginary direction of global time. And the massive particle will go there. So for the flat space time patch, the patch that is like the small I plus and I minus. So now I will briefly review the computation of soft factor from classical, how we compute a soft factor from classical soft theorem. So it was proposed by Sen and Ladha in 17 and 18. So one can derive the universal contributions in soft factors on asymptotically flat spacetime in 4 or more dimensions using the radiation arising from classical scattering processes in the vanishing frequency limit. So to take the classical limit, we have to consider that the external moment of Pi is much larger compared to the Planck mass. And in their work, it was shown that if we extremize a probability distribution of emitted multiple identical soft quanta in a given frequency bin, that is equivalent to taking a classical limit. And the classical and if you when we are maximizing the probability, we can find that the number of emitting multiple number of emitted identical soft quanta has to be very high. Then they calculated the energy radiated in that bin, which is like the frequency into the amplitude. and compared that energy with the classical formula for the energy flux in the long wavelength limit. Then that can be equivalently said that this is the statement of the classical soft theorem, where if we contract polarization tensor epsilon mu nu with the metric perturbation, or like the Fourier component of the metric perturbation, then you will get a sort factor up to a phase. The phase is like e to the power I omega r by 4 pi r. So the statement of classical soft theorem is that the Fourier transform of a radiative field at long distance is proportional to the classical limit of a single soft factor, where momentum and angular momentum operators in quantum theory are replaced by their classical counterpart. So similar to the soft graviton factor, one can also define the soft photon factor, where you have to contract the polarization vector epsilon mu with the a mu tilde, the electromagnetic field, and you will get the soft factor up to a phase. So during this computation of soft factor, in general, the scattering process, we have to parameterize the initial and final asymptotic trajectories of the probe particle or hard particle. So in d greater than 4 spacetime dimension, in general, we can write that the asymptotic trajectory, we can parameterize it as like r equal to vt. Because we assume that at flat spacetime at large distance, these probe particles are free, asymptotically free, there is no interaction. But when we consider 4 spacetime dimension, a non-relativistic particle in a radially outward trajectory experiences a inverse square force law. So that means the acceleration is proportional to 1 by r square. So now if we put back this r equal to vt parameterization, we see that this equation is not satisfied. So to account this long range force on the initial or final trajectories of this probe particle due to the other particles, we have to add this BLNT term. And if we add this BLNT term, then the above equation m d2 or dt square equal to minus k by r square is satisfied. So that implies that if we are considering a scattering process in 4 spacetime dimension in asymptotically flat space, so due to the long range interaction, presence of long range interaction, we have to also consider a log term in the asymptotic trajectory. So we can rewrite these trajectory equations in a covariant notion, where this xi u mu is like the denoting the trajectory, and this tau are the proper time. Similarly, we from this trajectory, we can calculate the angular momentum of the probe particle. And so the naive guess that how do we calculate this soft how do we calculate this dependence of on frequency? So in general, we just replace the tau by omega inverse. So here we can comment that we have now a ln omega inverse term in the soft factor. So in general, the power series expansion is breaking in this order, and so the subleading soft factor is a breakdown of a power series expansion, and we have to consider some non-analytic term like log.
Just try to understand the log term. I mean, it comes from that equations of motion, is it? I mean, you
It comes from the
this equation.
asymptotic trajectory of the hard particle. So if we consider this equation, and now
I mean, this Newton's law. I mean, this one.
yes. So now we will just for a zeroth order, we will put back here Vt, and then if we just so it is going like 1 by t square. So we are just integrating out and choosing the proper constant, and then we can see that like after doing the taking the integration twice, we will get a LNT kind of a term. Yeah.
That's good.
So contrary to the general belief, the soft factor must contain non-analytic terms in omega in 4 spacetime dimension, and the expression for soft photon factor and soft graviton factor looks like this, where SGR0 is the leading order soft photon factor, so that is like 1 by omega order, and SGR1 is the subleading order, which is ln omega inverse. Similarly, SEM0 is the leading soft photon factor for the flat spacetime, and SEM1 is the subleading order soft photon factor at the flat spacetime. So now I will concentrate on our work. So whatever we have done first, we consider a probe scattering on ADS space-time. So we consider a ADS black hole space-time. So in our first work, we consider a ADS Schwarzschild black hole background, and we calculated the soft graviton factor. And then we carried out the calculation for the ADS Reisner-Nosdam black hole background. So our probe particle has a mass small m and charge small q. The black hole background has black hole mass is capital M, which is much larger the probe mass, and the black hole charge is capital Q, which is also much larger than the small q. And we have considered a large impact factor, and we consider the cosmological constant is very small. So our calculations will be valid in linear order of cosmological constant. So begin with the gravitational action, which consists of the Hilbert action and Maxwell equation, a Maxwell action. Then we vary the action with respect to the metric and the gauge field, and we attend the equation of motion, the Einstein equation and the Maxwell equations. So our background metric for our computer, so for our help in computation, we consider our background metric in isotropic coordinates. So in isotropic coordinates, the temporal component G00 takes this form and the Gij takes this form, where we have, and the the zeroth component of the gauge field is A0, which is goes like Q by R, and in the so there are two perturbative parameter. One is the capital mass M, which we will rewrite in terms of phi, and the other perturbative parameter is 1 by L square, or the capital lambda, that is like the cosmological constant. So as we are interested only in up to order of 1 by L square, so our calculation we have truncated, or we kept terms up to 1 by L square order. So for that reason, our regime, our whatever the scattering regime, or whatever our computation is valid in this region, where the capital R is much less than the ADS radius, the M is much less than capital R, and the capital Q is less than M. So I have already mentioned that this resulting metric will describe the spatial slices of ADS only up to 1 by L square order. And as we have considered large impact parameter, so the capital M by R is much less than 1, and the other limit I have already mentioned, that is R square by L square is much less than 1. So now we have the background. So our next job is just we will linearly perturb this spacetime by introducing a point massive charge particle, which is traveling on an unbound trajectory. So the point particle action is given by this equation. And from the variation of this action, we can derive the stress tensor and the corresponding current. So in this stress expression of the stress tensor and the current, the delta is the covariant delta function. And we have normalized this covariant delta function in this following manner. So the introduction of this probe particle will perturb the background metric field and the background gauge field. So the background metric field G mu nu is getting a perturbation delta G mu nu. For we have just rewrote this G mu nu in terms of E, where the E is the trace reverse metric perturbations, and A, the delta A is the perturbations in the gauge field. So that we have denoted by small a. So now we will solve our equation of motion, this perturbed equation of motion, using the procedure which was proposed by Peters in 1970s. So he has done the calculations just for a Schwarzschild black hole background, and we have now, and he has considered the black hole mass as a perturbative parameter around the flat space time. So now for our case, there are another perturbative parameter, which is the cosmological constant. So the perturbed Einstein equation takes this following expression, and the perturbed Maxwell equation takes this expression. So in both of these equations, we have just kept terms up to 1 by L square and up to linear in M. So how do we solve this equation? So we use the Singe one function to solve these equations. So in Singe one function formalism, if it is very helpful to solve the equation of motion on a curved background. So there the Green's function is in general defined in terms of this wall function, and the wall function is half of a square root of a geodesic distance between 2 points. So one can calculate the corrections to the flat space-time Green's function, which we can name as tail terms. Due to this,
so defining a world function, so that assumes in some sense that you're only considering spherically symmetric type of, or some sort of, it preserves some isometry of the back, some symmetry.
Yes, this
and that's enough for our you to get the result that you're looking for, is it?
Yes, because ultimately the soft factor is like a sort of universal and coordinate independent.
Okay.
So this choosing this isotropic coordinate was just for the calculation help. And so using this sinh-Wald function, we computed the tail terms to the flat space Green's function. So there are two tail terms. One is the tail due to the black hole mass, and another tail is due to the ADS potential. And then the next step, using this Green's function, first we in this equation of motion, first we solve the E's in zeroth order, and we put back the zeroth order solution and treated the other terms as a source term, and then we got the solution in terms of this GM and GL. And then the next step is just to do the Fourier transformation of this metric perturbation and the gauge field perturbation, and then we take the soft limit. So the soft expansion, to do the soft expansion, I have already mentioned that we are considering a double scaling limit. So that means that omega 10 goes to 0 and L goes to infinity, keeping omega L finite. And
I mean, this Green's function, I mean, to understand, is it the Green's function for a particle? I mean, for a scalar particle?
Yes, it's like first we compute it as it's a scalar Green's function, and then just so this is a scalar Green's function. So for when we are considering the Green's function for H, like for the metric perturbations, we have to just change source term, so like we have to just properly parameterize a source term Fs. So
I mean, it's, of the wave, scalar wave, right? I mean, in the sense, it's like a Laplacian, Green's function of the Laplacian.
Yes.
I think that's Justin. I think that is my question. My question also. I think she's solving for essentially a one-dimensional version for the wave equation, where it's for the world, the world length. That's where the wave equation is being solved for. That's what I understood, at least if I'm not wrong.
Okay.
So, and is that correct, Arpita? I don't know.
So it's like first we solve for a scale, like we consider a scalar equation on this ADS spacetime, and it's not like a one-dimensional thing, but there are certain gauge choices, and we are
the dependence on the space-time coordinates only arises through the fact that the world function. That's the point.
Yes.
That's the sense in which it is one dimensional.
Yes, because the Green's function is like a sort of a delta function of that wall function, and so that way you can think. Yes, sure. Yeah, and so the basic building block of the Green's function is same for the scalar and or like the photon or the graviton. So there will be some additional terms, like in general, like we will take this H equation and we will see that the similar terms with the scalar equations, and we treat the other terms in a certain manner, and then we can rewrite the Green's function for like the H mu multiplied with something behaves like a scalar, sort of that way I can say. Is it clear?
Yeah.
So.
But in just ADS space, these Green's function are known, right? I mean, if there's no black hole.
Yes. In ADS space, the Green's function is fully known, but here the presence of black hole was a problem. So for that reason,
you're treating perturbatively, like you're putting. You're perturbing it from m equals 0, right? I mean.
Yes.
So can't you use that Green's functions which are known exactly and perturb those?
We tried, but the problem was like we are not trying getting any exact solution. Like
Uh-huh.
it was not sort of converging. So like the integral was not we are not being able to do. So then we thought that we will treat this as a perturbative. Like first we tried to do for the full space time,
Okay.
and we were not being able to find a proper thing. But now I think there are some other work have been considered, but that is also not in the presence of black hole. So in the presence of black hole, that was a problem. So for that reason, we truncate thing. And in general, like if I am considering the whole ADS space-time, and if we are converting it into isotropic coordinate, so it gives us a complex metric. So, so that was also a problematic thing. So for that reason, we started doing things perturbatively.
Okay.
Yeah, so during this soft expansion, we also have to consider an asymptotic limit where the observer distance is much, much larger than the probe particle position or like probe particle trajectory. And in this limit, we can simplify the distance between the probe particle and the asymptotic observer in this way, where this n cap is the direction of the observer, the unit vector along the direction. And so now the main point is like that we have to parameterize the asymptotic trajectory of the probe particle and its velocity as t goes to plus minus infinity. So I have already explained that in flats in d equal to 4, due to this long range interaction, there is a LNT term. But in ADS, for ADS case, if we consider the Gauss law, and then using the Gauss law that the total amount of flux through any sphere must be a constant, we can compute the potential, and then that from potential we can calculate the force, and from that force we can see that for ADS, if you want to for ADS potential, if you want to parameterize the asymptotic trajectory, that will goes like this 1 by L square T square, and the velocity will goes like 1 by L square T. But the expressions for the metric perturbations and the gauge field perturbations are already at 1 by L square order. So now if we consider these red terms, so then our calculations will go like 1 by L to the power 4 order. So we did not consider this term. So and this also implies that up to 1 by L square order, the hard particle asymptotic trajectories are same as flat space time trajectories. So there is no interactions due to the ADS space. So for rest of our calculation, the asymptotic trajectory will be the same as the flat space time. So the another trick we have to use, that which you have already mentioned, that like we will choose the polarization vector such that the gauge invariance of the electromagnetic the soft photon factor is intact. So so if we see this equation, this epsilon alpha a alpha equal to n prime SEM. So if we want to keep this equation invariant under epsilon mu going to epsilon mu plus k mu, so that will impose a constraint that k mu a mu tilde equal to 0. And we can also from this can understand that a0 tilde can be determined from ai tilde, and this allows us to choose the epsilon 0 as 0. And similarly, up to the arbitrary, the other, in addition, these expressions for mu tilde, as it is determined only up to a choice in gauge. So we can parameterize this our gauge transformation, the arbitrary gauge transformation. So we can write it as delta mu tilde equal to lambda k mu. And to be invariant under these transformations, we can see that k mu epsilon mu is 0. So that implies that if our AIs has any, if AIs is proportional to KI, those terms are not going to contribute in the sort factor. So keeping these two things in our mind, that the epsilon 0 is 0 and Ki epsilon I equal to 0, we can contract the polarization vector with the expressions of the gauge perturbation, and we can get the soft factor in terms of these betas, where these betas were introduced in this asymptotic trajectories. So we can see that the first line is the leading soft factor. So this gamma square is like omega square L square. So I have already said that our soft limit implies that we will take omega tending to 0, L tending to infinity, keeping omega L finite. So this gamma square is a finite and a big quantity, but and the first line is the leading soft factor because it is in the order of 1 by omega, and the second line is the subleading soft factor, which is of the order of ln omega inverse. So this result can be expressed in a more compact notation. So if we rewrite the initial and final trajectory of the probe particle in this manner, and the asymptotic momenta of the probe particle before and after the scattering, so we can then rewrite also the asymptotic angular momenta in terms of this trajectory. And so then,
So I have a sort of related question. So if in the case of, for instance, something like Leonard Witcher potential or something in
yes,
a
yes,
flat space, we know that it has this antipodal identification.
matching condition.
Yeah. So do you, from the expressions that you wrote down, do you have any statement about what happens to what is the generalization of that to ADS?
But is like when we are calculating, so in general, when we are going to the flat patch, the antipodal matching condition will hold.
Will still hold. So for
Yes.
you, order by order, this statement is still true. Is that
Yes,
correct?
yes.
So which also means that what is the ADS origin of antipodal identification is something that it's
But
still.
I don't think that at the next order it is a doable thing following this calculation, because I have already
Yeah, the 1 by
mentioned.
L4. Yeah.
Yes.
Yeah,
Because at
mixing.
1 by L4 there is like that we can't assume that the trajectories are free anymore.
Yeah, no, that's fine.
So,
I'm just saying that,
yeah.
but this strategy somehow seems to me to be suggesting that you will not actually be able to see what happens. What is the origin, in some sense, of the antipodal identification in ADS? I think we won't be able to see. Is that correct?
Yeah, like in ADS, no, but in flat patch, yeah. So
Right. I mean, yeah.
yes,
No,
yes.
this calculation is completely fair.
Yes,
Yeah.
yeah.
Thanks.
Yeah, so doing this rewriting, we can write the leading soft factor and the subleading soft factor in a more compact notation, where here this you can see that this epsilon mu p a dot k was like flat space time thing. So now it is like a flat space time soft factors, but multiplied with this factor, which is like a p vector square by p dot k square. So this is a new result what we found. So now I will proceed to the second part of the talk. So here, so till this point of time, everything was classical calculation. So now what we have done, so the leading soft factor can be expected to be universal, and it holds beyond tree level. So this allows us to determine the large gauge word identity following its known equivalence with soft photon theorems in asymptotically flat spacetime. So in our case, this 1 by L square correction can be considered as a perturbation of the flat spacetime result. It is realized across null infinity on the flat patch around the center of the ADS spacetime. So this is the ADS metric, the figure is drawn in terms of this global coordinate. And we will use this 1 by L square corrected soft factor to determine an equivalent perturbed large gauge word identity. And we hence find that the specific corrections to the soft photon mode and the gauge parameter that realize the equivalence of the large gauge word identity and soft photon theorem for the leading soft factor up to 1 by L square correction. So first I will give a brief review of this soft photon in flat spacetime, how one relate the soft photon theorem and the word identities. So this was work was mainly done by Strominger and his collaborators. So if we start with a Penrose diagram of a Minkowski spacetime, So we know that the radiative gauge fields like AZ bar, those does not die at the null infinity, because the Lennard-Wishart potential, if you take your Lennard-Wishart potential or the force to this null, the limit such that you go to the null infinity, we can see that it exists, the angular dependence still exists, and you can't make it zero. So now if we assume that there are these charges q epsilon plus and q epsilon minus, which are defined at this null infinity of this Minkowski sky plus and sky minus, the asymptotic null infinity. So these charges then satisfy the conservation equation that q epsilon plus has to be equal to the q epsilon minus. And the expression of q epsilon plus and q epsilon minus is given in terms of the gauge parameter epsilon and the electromagnetic field strength F. And these two charges are defined as the sky plus minus and sky minus plus. So that are the end points of the sky plus and sky minus. So we can rewrite this, we can use the Stokes law, and we can change these integrations to the such a way that such that now we can consider the q's on the whole surface, whole null infinity, and then we can rewrite those charges as a sum over soft and hard contribution. So in this expressions, q epsilon plus, the NF are the soft photon modes, and the qk epsilon zk z bar, the whole thing is like a hard contribution. So qk are the hard charges with coordinates z and zk and zk bar. Sorry, there is a typo on the celestial sphere. And the soft photon mode number modes can be written in terms of this field strength. And given a scattering process, we know that the charge conservation implies that this implies this equation, and from this equation we can show that. So this equation, if we now put back the expressions of q epsilon plus and q epsilon minus, and if we do a little bit manipulation, one can show that this is the large gauge odd identity. So the left hand side is only fully terms of this soft photon mode, and the right hand side are the hard charges. So now to establish the connection with the soft theorem, so first we will write the expression of the soft photon mode del z nf from the mode expansion for Az. So here the A plus and A minus are the like the creation and annihilation operator. And then if we assume the expression for the gauge parameter epsilon as 1 by W minus Z, we can see that this odd identity, sorry, this odd, we can see the odd identity will take this following expression. And doing some manipulations, we can show that, so if we are writing a soft theorem in this manner, where the S flat EM is the soft photon factor, so the main goal is like that, we can show that this equation, this equation, and I think my pointer is, so here I need the pointer, okay, but this 4 d2z dz epsilon, this equation, and these equations, this limit omega goes to 0, omega a plus fs in these equations are equivalent. So to show that, one has to first substitute the soft photon momentum and polarization in terms of the null momenta q mu, and then we can choose this parameterization. So we have chosen this parameterization from the Strominger paper, and we can rewrite our soft factor now in terms of this zz bar coordinate. So this zz bar is the soft photon direction, and doing the manipulations, one can show that this large gauge odd identity is equivalent to the soft photon theorem. So now what we will do, we will just take a 1 by L square perturbative corrections to this expression. So we will demand that now with the A plus flat, which was a creation operator of a soft photon at the sky plus, now we also have a A plus tilde due to the ADS corrections. And so now as we are considering is as this correction is a perturbative one. So in the left hand side, we introduce this A plus tilde, which will correspond the soft photon mode due to the ADS correction. And in right hand side, this SL0 EM is the soft photon for the correct 1 by L square correction to the flat space time soft factor. So then we can rewrite our soft photon factor expression also, the 1 by L square corrected soft photon factor expressions also in terms of null momenta. And then that expressions will take this following these expressions in terms of Z and Z bar. So here the gamma was introduced earlier, which was the omega L, which is like a finite and big quantity, and 1 by gamma square will be treated as a perturbative parameter on the flat space-time patch. So doing this to show this to hold this equation. So if we want to get this equation, so we have to introduce now corrections to the epsilon, the gauge parameter, and the soft photon mode. So we find out this expression. So these are the corrections. So if 1 by L square, if the corrections was into the gauge parameter is also of the order of 1 by L square. So epsilon L is that correction, and the expression of epsilon L goes like this, which is little complicated. So here it is like that. One thing is that it is not a holomorphic like the flat space time anymore. Now there is a mixing between this holomorphic and anti-holomorphic thing. But at the end, we can retrieve the 1 by L square corrected soft theorem, provided that our soft
This
photon
is
mode,
Z.
sorry,
What Z is a coordinate on the Celsius.
celestial sphere, yes,
Yeah.
yes. Yeah. So this soft photon mode now has two part. One was the previously the flat space time mode, that is like this del z nf, and we have now corrections to that. So here we can observe that there are two terms. We have to write n1 ADS and n2 ADS. So why we are getting these two terms? Because when we are considering it's like a flat space time plus correction. So when we are considering this 1 by L square correction to the epsilon, and we also are considering a 1 by L square corrections to the n, so there is a mixing between the flat space time epsilon n and the flat space time epsilon and 1 by L square correction of n, and similarly a 1 by L square correction epsilon and flat space time n, and those two terms ultimately have to cancel out to get this 1 by L square corrected soft theorem. So to do that, we have to introduce two kind of a modes, N1 ADS and N2 ADS. So this N1 ADS is completely in terms of this A plus tilde, which is the corrections, the 1 by L square corrections to the flat space soft photon mode, or like the creation operator, soft photon creation operator. And on the other hand, this N2 ADS is there just to cancel out the mixed term. So that is the main crux here, that the del z n1 ADS helps to recover the soft theorem in at 1 by L square order, and then del z n2 ADS is a consequence of a perturbing about flat space time. Like this little later, I will show that this term we will not receive this term when if we are considering a large ADS radius limit from a of a boundary CFT correlator. So there only N1 ADS only will come. So the basic difference, like if we are considering a 1 by L square correction to a flat space time, and if we are taking thing like a flat space time limit or like large ADS radius limit from ADS, so there are this difference, that this of N1 N2 ADS. So this was the 1 by L square corrections to the flat space large gauge word identity. And now I'll go to the last part of our work. So this is the work which is almost near completion. So there we tried to get this large gauge word identity, this 1 by L square correction to the large gauge word identity from the large ADS limit of a conformal word identity. So we already know that if we have a ADS4 spacetime bulk, and if we have a bulk gauge field mu, it is dual to a CFT at boundary with a U1 symmetry, and the current at the CFT, which is J mu, which is dual to the bulk gauge field A mu. So in the absence of a magnetic charge, this CFT word identity, like if you want to keep our correlation functions invariant under the U1 transformation, we can get the word identity. So this word identity, in this word identity, J mu is the conserved current, and there are two coordinates are introduced, x1 and y1. So the y's are denoting the past scatterings, like the past. So the thing is like we are assuming that the scattering region is at the center of this ADS space time, around tau equal to 0. And in general, if we are considering a global coordinate, so our global time runs from like tau goes from -5 to +5. So when we are trying to construct a scattering state, like photon scattering state from these CFT operators, so we will consider the incoming states will cover the global time -5 to 0. So at that region, the operator insertion are done at point the wise, and the outgoing state will be correspond to the global time of 0 to pi of the CF of the boundary, and that boundary, so for the outgoing state the position are like the x prime, and q are the charges corresponding to this conserved current. So now we will take this word identity and we will consider an integrated version of this over, and to do this we will introduce an arbitrary function alpha over the boundary coordinates, which are denoted by these prime coordinates tau prime and z prime, and we can rewrite the CFT word identities in this way. So in large L limit, it is a well-established fact that certain correlation functions goes to an S matrix element. So it was very explained in details in Kaplan and Fitzpatrick work, and recently also in Hijano's work in 2019. So if you look at into this word identity, this equation, this integrated expression of the word identity. So here we have to find the equivalence between this alpha x prime and the gauge parameter epsilon z and z dependent on z and z bar, which I show in the earlier transparencies. And so on the basis of this equivalence, we can show that the right hand side of the word identity will goes to the right hand side of the flat spacetime soft theorem. And the left hand side of the word identity one can determine using the HKLL constructions. So we know that if we consider a scalar field or any field in a ADS spacetime, and if we solve the equation of motion, we will get two modes. One is normalizable mode and one non-normalizable mode. So this normalizable mode is associated with a boundary current J mu, and then we can rewrite this A mu operator, which is in terms of this J mu following the HKLL kernels. So in these equations, the K's are the HKLL kernels. So the next step is that we want to construct scattering states like creation and annihilation operator on the null infinity of the flat patch or near the scattering region, which is placed at tau is equal to around tau equal to 0 region. So we can construct that creation or annihilation operator from this capital A mu operator following this formula. So this is the goal. So first we are taking a CFT word identity on the boundary, and then we are solving field equation, classical field equation on the bulk, and using the HKLL construction from the boundary current, we are constructing creation and annihilation operator on the flat patch, and then from that creation and annihilation operator, we can show that in this large L limit, the CFT correlation functions will, or the CFT word identity will give us the Weinberg soft theorem. So now I will just briefly explain that what are the implications of large L limit. So if we start with a metric in global coordinates, and then if we introduce a coordinate transformation, we can see that in large L limit, so this metric goes like a flat metric. So, and whatever HKLL kernels I just shows in these earlier transparencies, this case. So this case involve factors which goes like e to the power I plus minus I omega k dot kl tau minus tau prime. So we know that this omega kl is like discrete because of the as ADS is behaves like a box and the spectrum is quantized.
Yes, hold on. I mean, the previous conclusion that so you have shown that the U1 word identity in the boundary, I mean,
Yes.
corresponds somehow to the Weinberg soft theorem in the bulk. I mean,
Yes,
for
yes, yes, yes.
that's
The large, yeah,
1 by L squared thing. Now,
yeah.
of course, there are other word identities, right? I mean, the stress tensor word identity and so on in the boundary because it's a conformal theory. So
Yes.
there is stress tensor. So that you expect it to be correspond to some graviton-soft theorem. I mean, there.
Yes. But yeah, soft graviton theorem. Yeah, we expect that, but that calculation, like that computation, like is not done in the literature yet. Yeah.
But in the flat space case, there was somehow an infinite dimensional version also, right? I mean,
Yes.
though, but in this ADS, higher dimension ADS, you don't have infinitesimal, infinite dimensional symmetries.
Yes. So the fact is like that in the so in when we are in the boundary, it is like a we know that it is a finite. Sorry. Yeah. So it is a just global U1 symmetry. But when you are considering this large L limit, so it is giving you a large gauge transformations at the flat patch. So that is happening because one reason is like this double scaling limit. So for this double scaling limit, one can see that the dominant contributions is coming only from the tau equal to pi by 2 regions. So
So somehow you're saying that somehow
yeah.
this double scaling limit, you're losing all the infinite.
Yes, the finite nature of things, and it is making things infinite.
Okay.
Yeah.
So yeah, this is just the opposite. In the flat space, there are infinite dimensional version. Current algebras, but here you don't have. In the ADS case, you don't. That's
No. Yeah, at the boundary, we do not have any,
yeah.
like for this case, as we are considering CHEP-th, we have a finite dimensional symmetry. But when we are taking this double scaling limit and we are going to this flat patch, so I think this is now a very known result in other aspects. If you see that now in this work by Grumiller and Sheikh Jabari, they have also shown that if like in any space time, if we have a surface, if we have a time like boundary kind of a thing, so there we will always getting a finite dimensional symmetry. But if we construct if we go to a null surface at any point of the space time, suddenly the symmetries get enhanced.
But somehow all this argument should break down in ADS3, right?
It is 3. Okay.
Because ADS3 has infinite dimensional algebra.
Yes. ADS3 has infinite dimensional algebra, and ADS3, yes. So there it says the boundary, the CFT, yes. So the what identity is also representing infinite dimensional symmetry, and
Yeah. So this
yeah,
L going to infinity limit. Somehow this argument that the infinite dimensional symmetries of flat space are not preserved in this L goes to infinity should break down in ADS3.
yes. But yeah, but these compute like yeah, like Hijano, their first work was done in 3 dimensions, and but then I think there were some subtleties which I have not gone through properly.
As far as I understand, the
Yeah.
map from the boundary in ADS to the the scaling limit that one takes, it is not it's not one to one or in one to one on two or whatever that is.
So it
So I
is
think that
dependent on the space-time dimension.
well, the space-time, yeah, for example, but but anyway, in flat space in 3 dimensions also you have an infinite dimensional algebra, right? So it's like
Yeah,
even
and
if you
like
start with
for
ADS3 and you
yeah.
get, I think they do get BMS3 there.
Yeah. There you get the BMS3, but there the thing like so there the thing is like that we are going from a infinite dimensional algebra to a infinite dimensional algebra.
Yeah.
In this case, this is like from a finite dimensional thing we are going to a infinite
No,
dimensional.
but I think it is finite dimensional and it remains finite dimensional. So I think whatever you can see on the boundary of ADS, you can see also in this deep in the middle of ADS by doing this double scaling limit. But whatever extra stuff that is truly flat space, I think this double scaling limit sort of misses it. This is what I understood from that paper. So
Okay.
is that? Would you
Okay.
agree with that statement?
Yeah,
No.
this part actually is not clear to me. Like how I
Mhm.
supposed to understand that. Like because the expression of epsilon is still same, like the when we are identifying between this alpha and epsilon, the gauge parameter, so the
Mhm.
gauge parameter is still like dependent on this that's the same expression for flat space time, 1 by epsilon minus z, 1 by z minus w, and I think that represents like that you have infinite number of epsilons.
Mm-hmm.
So I thought that it was infinite dimensional. So, but
I see. Okay.
for me it was like whatever I was getting a, like I was thinking that as only tau equal to pi by 2 slice, like as we are just concentrating on, like we are just fixing the global time. So sort of now whatever final result we are getting, it is like sort of dependent on z and z bar, and when it is just z and z bar dependent, so that is like we can think like it is sort of a infinite dimensional
Right. Right.
symmetry.
Yeah.
Yeah, but
Okay.
for our
I had a slightly different question. I think it may be from the previous slide. Can you go back to
okay,
the
okay,
previous
sorry,
slide?
sorry. Yeah,
Uh,
this
yeah. No, the one before this.
this one.
Yeah. So no, no. Yeah, a little bit more up, up, up. So here, so this all of this expression that you have written here, this is basically you're starting from ADS safety, and then taking some space-time type of limit, right?
Yes, yes. So the
So
yeah.
is there some advantage to doing this in Mellin space? Have you thought about it or something like that? Because I
Yes,
think
yes. Like I was thinking, and I'm not sure about it, but I was thinking that whatever expressions of A I like kernels, whatever I got, like I have now an expressions of A up to this 1 by L square order or this thing.
Mhm.
So I can do a Mellin transformation in omega variable, and I have to check.
So
Like yeah, I
yeah, I
thought
think
of it,
it
but
may be interesting because I think that you will directly find some map to the null infinity of flat space, right? So that I think would be useful to kind of see if there is if this is a bit forced in the sense that you're working with coordinate space on one side.
yes, yes,
And anyway, yeah, I mean maybe we can talk about it later. Go ahead.
yes, yes, yes. Okay. Where was I? Yeah. So yeah, so now the main point like is like the HKL kernels involve this e to the power I omega kl tau minus tau prime, and this omega kl is a discretized, so that is like and where this energy levels kappa runs over all positive integers. So the point is like when we take a larger limit, so we expect that we will obtain a continuous Minkowski modes which will arise from this discrete ADS mode, and the kappa, so thus the kappa, the energy levels will have large values. But then one can see that to have these HKLL kernels to stationary solutions or like proper stationary solutions, this omega KL has to scale with L. So for that reason, we have to rewrite that omega KL as omega L. So again, this double scaling limit enters here in this way of work. And we can see that now in this way, we can take omega continuous. So we can take omega goes to 0. So the main thing is like first we have to take L tending to infinity limit and then omega tending to 0 limit. So this thing is similar to our previous analysis where we considered omega L as large and 1 by omega square L square as a perturbative correction. And now as the energy levels are very large, so the sum over energy levels now can be treated as an integral over frequency omega. The other point I want to mention that in large L limit, HKLL kernel also involve a factor like e to the power plus minus I omega L pi by 2. So this is the main, so now when we have an integration over a global time, so the integration looks like this e to the power plus minus I omega L tau prime minus pi by 2. And in double scaling limit as omega L is very large, so we can see that in this from this integration uh, the only tau equal to pi by 2 regions, sorry, tau prime equal to pi by 2 regions will contribute. So we can ignore other contributions from the other global time region. So that was one important fact of this taking large L limit. So then it is easier to follow that we can now construct. We assume that there are no Coulombic fields like a tau or a rho, because a tau and a rho will go to that Euclidean cap. So we are only interested in the radiative modes like Az and Az bar, which will go to the sky plus of the flat patch of the center at the center of the radius. And we can find that the relation between the outgoing creation mode and the current, so that has been derived in this paper by Hijano and Neuenfeld. And so now you have to just find the equivalence with the flat space time gauge parameter, and we can see that the conformal word identity will give us the Weinberg-Soft theorem. So this part, till this part was done in Hijano and Neuenfeld paper. So whatever we are doing, we are again doing just the 1 by L square correction. So like we are just keeping terms up to 1 by L square order. So the HKLL kernel involves these terms. So when we take a large L limit and if we keep terms up to 1 by L square, so these expressions now have additional contribution. And those additional contributions will give us the 1 by L square corrections to the large gauge word identity. So we have already achieved a contribution to outgoing soft photon mode A plus up to 1 by capital L square. There is a typo. So one point we have to remember that J mu, the boundary current J mu has no L dependent. And we have found a soft number mode that agrees with our previous analysis and a gauge parameter involving additional corrections. So we hope this result to communicate in a forthcoming paper. And I have already mentioned that in these calculations, we did not find any N to ADS mode, which was required previously to cancel out the mixed terms. So we have just received the N1 ADS. So these are the main theme of the work. And so far, I will just summarize my talk in some points. So we studied the classical scattering of probe particle on the ADS black hole background. Then we consider a cosmological constant as a small perturbation around flat space-time. We defined a soft limit, which is a double scaling limit. We extracted out the soft factor from the solutions. And then our analysis provides a linear in lambda perturbative corrections to the flat space-time result. And using this soft photon factor, we interpreted a soft theorem and corrections to associated gauge word or associated large gauge word identity. And also we relate this large gauge word identity with a CHEP-th word identity in the large EDS radius limit. Thank you. Am I audible?
Yeah, thanks.
Should I stop sharing?